Today we have with us Dr. Joyce Guzik, who is a laboratory fellow in the Nuclear Threat Assessment Group and the XTD division at Los Alamos. She received a PhD in astrophysics from Iowa State University in 1988 and joined Los Alamos in the same year. She has continued research in solar and stellar evolution and pulsation modeling since then, working with a number of colleagues, students, and postdocs, co-authoring over 70 refereed articles and over 200 conference proceedings papers in this field. She has pursued interest in testing stellar interior physics, including opacities, using comparisons of models with pulsation observations. I'm pleased to have us with us today, and I'm looking forward to her talk. Also, I should mention, make sure everybody knows that this talk will be recorded, so anything you say will be part of the video. If you have any questions, please try to enter them into the chat field, and I will read them at the end. Otherwise, please take it away. And thank you, Joyce.
Okay, see if I can share. Trying to share my content, but let me try this. Okay, so it's on, I believe it's on full screen. All right, and everyone can hear me okay?
Yes.
All right, great. Well, thank you for the opportunity to present this talk. And it's going to be about how we make solar models, and there will be some about how opacities affect the interior structure of the sun and comparisons with the field of helioseismology, where we're able to infer what goes on the inside of the sun from the stellar pulsation modes. Why is it not advancing? There. Did I want too many? Okay, so the solar abundance problem. Until the year 2004, when I actually had, before that, actually had stopped working on solar models, we thought we knew very well the interior structure of the sun and how it reached its present state. But new analysis of the sun's spectral lines in 2004 was actually, the paper was published by Asplund et al. In 2005, revised downward the mass fraction of elements of heavier than hydrogen and helium, particularly the abundances of these abundant elements, oxygen, carbon, and nitrogen. So then when we re-evolved models calibrating to these newly determined solar photospheric abundances, they gave worse agreement with helioseismic constraints. And you'll see many times this picture on the right, which I will explain more about the sound speed difference between a standard model and that inferred from the sun, from the surface on the right all the way to the center on the left. And the picture shows the old abundances, and the agreement was a lot better. And now with these new abundances from 2005, the discrepancy is much larger. So there are also a couple of other helioseismic constraints. We care about the bottom of the convection zone, where that's located, and also the envelope helium abundance in the sun's convection zone. So how can this discrepancy be resolved? And should we adopt these new abundances, or is there some other problem with our modeling? So at the end of the talk, I hope to save some time for discussion about which is the actual problem after you've seen these comparisons and this evidence. Is it really a solar abundance problem where we have that we don't know the sun's abundances, and maybe these new lower abundances aren't correct? The solar opacity problem, do we have not enough opacity in the sun, and is that making our models disagree with the sound speed in the interior? Or is it a solar modeling problem? There's some other input physics we're missing or we're getting wrong in modeling the sun that's causing these problems. So this problem's been called all of these things by different people in the literature. So I'd like to have a discussion about that at the end. So my outline for the talk is I'm going to first talk to you about how we actually make a standard solar model, what goes into it, what's left out. How do we get the constraints from helioseismology or solar oscillations? Some attempts to reconcile the models and observations, different input physics we're going to try changing to see if that improves things and is that believable. And I'm also going to talk about models using the Livermore Opal opacities, which I've used almost exclusively up until 2015 for solar interior modeling. But in 2015, 2016, the LLNL LEDCOP opacities came out, the newer opacities. So I'm also going to show you solar models calibrated with both of those and show you what the difference is with this compared to the constraints. So the surface composition of the sun is very different than composition of elements that we might find on Earth. The sun is 73% hydrogen, this picture on the left, about 25% helium by mass, and only 1.8% other elements. And that's true with the old abundances. With the new abundances, it's more like 1.2 or 1.3% elements heavier than hydrogen and helium. And if you look at the breakdown of those 1.8% other elements, about a third of it by mass is oxygen, followed by carbon, neon, nitrogen, magnesium, silicon, iron, sulfur, and all the other elements, the heavier ones than iron, are here in the other 1/3 by mass. So oxygen is very important, as is carbon and iron and nitrogen in the solar composition of elements heavier than hydrogen and helium. So in 2005, Asplund et al. Published a new determination of the solar abundances. And this is not from any change in the sun itself, but really a reanalysis of the spectral lines with model atmospheres taking into account 3D models and non-LTE effects, and also in some updates to the atomic physics. And they derived an oxygen abundance that was 48% lower than the previous abundances by Grevesse and Saval 98. 35% lower in carbon. These numbers here that are published, they're a logarithmic scale relative to hydrogen, where hydrogen is 12. So it's 10 to the 8.6 over 10 to the 12 is the actual number fraction of oxygen, if you wanted to convert that. Nitrogen was 27.5% down. Neon and argon, these noble gases, they're not actually measured in the solar photosphere because they don't have any lines there, so they have to measure them at a higher temperature in the sun's chromosphere and then correct for whatever effects may be going on there to get the photospheric abundance. So they're a little bit more uncertain, but 74% decrease down in neon and 66% in argon. A lot of the other elements, sodium to calcium, only went down by 12 to 25%. Iron only went down about 12%. And this added up to a revised fraction of what we call metals, which is usually written by the letter Z. The mass fraction of elements heavier than hydrogen and helium is called Z, and it went down from 0.018 to 0.0122 in this new abundance determination. So I'd like to also show you these plots I made of the solar abundance determinations over the years. And in 1976 were the Ross-Aller abundances. This is a mass fraction of heavy elements compared to hydrogen, which is usually X in the literature. So you see that they were kind of low and then they went up in this 1989 determination. And about when I started making models, I was using the Grevesse and Knowles 1993 abundances. Then the Grevesse Saval 98 are over here. And then they went way down to the Asplund 2005. And more recently, they've come up again a little bit in the AGSS 09 abundances. And then there's another one from 2015, but it's basically the same as the one from 2009. So these changes in element abundances are larger in these determinations than the uncertainties published. So this isn't all just within the uncertainty. There are actually fundamental changes in the derivation of the abundances over time. So now I'm going to go a little bit into what goes into a standard solar model. So these are the ingredients that we put in. We do one-dimensional static models of the sun for a standard model. So first we need element abundances, how much of each element to put in. And of course that does change in the interior over time as hydrogen is converted into helium and some carbon is converted into nitrogen, and from this, a little bit of this carbon, nitrogen, oxygen cycle burning, and also the surface changes, but I'll talk about that in a little bit. We need opacities. We need not just the radiative opacities, but also have to add in conductive opacities. And usually opacity tables need to be supplemented by low temperature tables for the solar, near the solar surface, which include molecules and some other effects. So these three opacities have to be put into the solar model. The equation to state is needed. Nuclear reaction rates are needed. A convection treatment, because the sun's envelope is convective, the outer 30% by radius is convective. Diffusive settling and radiative levitation need to be included. Well, radiative levitation turns out not to be so important for the sun. A little bit, but not much. It is very important in other kinds of stars that have a smaller convection zone. But diffusive settling turned out surprisingly to be important with the sun. Even though that outer 30% is convective, at the bottom of the convection zone, elements can settle out, helium and heavy elements can settle out relative to hydrogen over the sun's 4.5 billion year lifetime. And that adds up to about 5% of the helium settles out of the convection zone, and about 5 to 10% of the heavy elements settle out. So that needs to be included in the models to get good agreement with seismology, or better agreement anyway. And also you need some kind of surface boundary condition or model atmosphere, which doesn't matter as much for the interior, but it's still important to make the standard model. So there's a lot of physics that's usually omitted in a standard solar model. Rotation is usually omitted, rotational induced mixing, magnetic fields, any kind of mass loss. The sun's solar wind right now is quite low, 2 times 10 to the minus 14 solar masses per year, so that's considered negligible. Convective overshooting, we just use the mixing length theory, as I'll show you later, to determine the bottom of the convection zone. Any mixing in momentum and energy transport due to the sound waves or due to any gravity waves that might be in the interior. Turbulence by instabilities, turbulent pressure and energy, these are usually omitted in the evolution and even often in the pulsation calculations. So these effects, they require some of them require multidimensional modeling, and some of them occur on timescales that are significantly shorter than the evolution timescale. So it's hard to put them in an evolution code where you're trying to model billions of years of evolution. You can't take time steps as small as a convective timescale, for example. And in some cases, a parametrized treatment has been implemented in 1D evolution models based on a 2 or 3D localized model. So models have been done that way to see the effects. So for the old abundances, the ones from before 2005, the simple spherical sun assumptions resulted in very good agreement with helioseismic tests. So these are one-dimensional. We assume an initial homogeneous composition. We have negligible mass loss or accretion after the sun arrives on the main sequence, starting to burn hydrogen in its core. No effects from rotation or magnetic fields, no additional mixing from any of these effects that we know are probably going on that are maybe important, and very simple surface boundary conditions. So the old abundances, these are the latest physical data, even some of this I still use up to the present day, produced models in good agreement with the helioseismic tests, but now the agreement is not so good. I had been using the Livermore opal opacities from 1996. These were supplemented by, at first, the Alexander and Ferguson 1995 low temperature opacities, but most recently we've been using Ferguson et al. 2004, and there's even updates to that now for the newer abundances from 2009. The equation of state, I have been using an analytical equation of state developed by Fritz Swenson, Alan Irwin, and and Rogers, and it was based on the Eggleton, Faulkner, and Flannery equation estate, but it included a bunch of other things like relativistic effects and Coulomb corrections and a few other things. So I don't want to go into that here, but I like it because it's analytical and I can change the abundances, and that automatically changes the equation of state. We're using the Nacre nuclear reaction rates from 1999 and a couple of reactions in the sun for the PP2, I3, and the CNO rates. We've updated a little bit from 1999, but otherwise those haven't changed much for the sun. We're still using the mixing length treatment from 1958 from Erika Bohm-Vicenza, and we include diffusive element settling. The treatment I'm using is one by a textbook from Burgers in 1969, and it was the results were published by us in 1988 for the sun. This includes thermal, gravitational, and chemical diffusion of elements separately, and it also includes, you can also separate these treatments for every element in the sun, so you're not just diffusing all the metals at once or everything at the same rate. So I like this treatment as well for that reason. So these are the equations that go into modeling stellar structure. And I don't expect you to understand everything in all of these equations, but I just wanted to show you that these are very simple assumptions. The first one is mass conservation. All the zones in your 1D solar model have to add up to the mass of the sun. The second one is hydrostatic equilibrium. The sun isn't exploding or imploding in real time. So the pressure gradient pushing outward on the gas has to balance the gravity pulling in, so it stays at a pretty constant radius. It's changing very slowly with time. Thermal equilibrium, and this is actually where the time derivative comes in here in this entropy term for the sun. So the sun evolves because hydrogen is being burned in the core into helium, and it's the energy generation rate here, and that's producing work and producing heat, and also there's a luminosity loss here out as this energy is traveling out of the sun. So here's just the thermodynamic equation where you have the heat absorbed in a section, in a cell or a zone, is equal to the change in internal energy plus the work done. So very slowly over time, the sun is evolving and changing its structure because of nuclear energy generation. And there's a couple more equations for how energy gets out of the sun. The first one is the radiative diffusion equation. So this is where this sets the temperature gradient in the inside of the sun, inside the convection zone. And here is where the Roscelin mean opacity comes in, right there. So in this temperature gradient. But if the temperature gradient gets too steep, it becomes more efficient for convection to carry the energy out of the sun. So then you use, if the radiative gradient is bigger than this adiabatic gradient, then convection takes over, and the outer 2% of the sun's mass and the outer 30% of the radius, so not a lot of mass, but a lot of the radius, is actually convective. And out there, the opacity doesn't matter. What really sets the structure of the sun is the thermodynamic, the equation of state, thermodynamic properties. So here's gamma 2, this thermodynamic derivative is related to the adiabatic gradient. So worry about opacities below the convection zone, but once it's convective, we really need to know the equation of state well to get the outside of the sun correct. So how do we make a standard model? Well, we divide the sun's mass into several hundred radial zones. You can do more or less, but several hundred is pretty adequate. You run the model forward for several hundred time steps from the time the sun starts to burn hydrogen in the core to the present time, 4.52 billion years later. And then you compare the model properties to the observations of the present sun today. So when you run this model forward, it had better end up with the sun's radius as we observe it, the sun's luminosity, the current mass of the sun, and the surface composition that's been determined, the heavy element abundance over hydrogen ratio that is measured from these spectral lines. And if this result disagrees, then we go back and we iterate. One knob we use is the initial helium abundance. We don't know the initial helium abundance of the sun very accurately. And helium is not measured like argon and neon either in the photosphere of the sun. So that number is uncertain and we can adjust it. And that's a good knob to just adjust the luminosity of the sun. Higher helium abundance gives you a higher luminosity. We adjust the Z abundance because the metals are settling out. So you want to start with a higher Z abundance, let these metals settle out, and at 4.5, look at what the abundances are. And if they don't agree, well, you have to put more or less metals in to get to calibrate to the current sun. And then the mixing length parameter, the mixing length to pressure scale height ratio. And that turns out to be a really good knob to tune the solar radius. And so you change these things and you rerun until you match these constraints. So these numbers are determined pretty well for the present sun. This is the solar radius. There have been recent papers in the last decade about lowering the solar radius, but most people haven't adopted the new radius yet. It's a determination from a different method. So instead of just looking at the sun and measuring and then knowing the distance. Luminosity is right here, and that does vary with the solar cycle a little bit, but usually only in the last couple of decimal places here. The mass of the sun is here. We know that very well from the Earth orbiting around the sun. The age of the sun, we get that from meteorites and moon rocks, so it could be uncertain by a bit. And we also have here the different photospheric element abundances that are our constraints. So before I used to use Grevesson-Knowles 93 or Grevesson-Saval 98, and then we switched over to Asplund et al. 2004, 2005, which is going to be labeled AGS 05. And then there have been a couple more recent determinations that are a little bit higher. This one is based more on meteorites for many of the heavier elements. So it's a little different from this one. And then this is the more recent one by that same group. Okay, so what happens when you run these solar models and you try to calibrate them? What are the input parameters and what are the final parameters you get? Well, here for the Grevesson-Knowles mixture, I needed to input a helium mass fraction of 0.27. I needed to put in a Z abundance metal fraction of 0.0197 and use this mixing length to pressure scale height ratio 1.77. And after the model is evolved to 4.52 billion years, the surface helium abundance, as you see, has gone down from diffusion to 0.242. And you can also look at where's the bottom of the convection zone. Where does the convection zone end? And it ends at this radius, 0.713, out from the center of the sun. And when you do the same thing with the Asplund mixture, you need less helium to calibrate to the luminosity. Here's the initial Z. You have to get that down because the Asplund abundances are lower. Here's the mixing length you need to get the solar radius. And when you let the diffusion happen over the 4.5 billion years, the surface abundance is helium is 0.227, and the convection zone is actually the bottom is higher up in the sun, so it's shallower at 0.731. Now I'm going to explain this next, but helioseismology has been able to tell us what the envelope convection zone helium abundance is today, and it's more like 0.248. And it's been also able to infer where the bottom of the convection zone is, and it's at 0.713. So these old abundances agreed better. They were very close to this helioseismic inference, whereas these new abundances, the helium abundance is too low, and the convection zone depth is too shallow. Okay, so I've got to go through, I think I'll just hit all these at once. It's doing it in steps. Okay, so I'm going to tell you a little bit about solar oscillations now and how these constraints are derived. Well, the sun is actually oscillating in thousands of acoustic modes in a kind of analogous way to this bell, except this bell is oscillating at 2000 hertz, whereas although the sun is oscillating at 2000 microhertz, so approximately the frequencies, the normal modes of oscillation. So they're about 1,000,000 times lower in frequency. And we can't hear them because we have no air between us and the sun, but people have taken these frequencies and sped them up 1,000,000 times, and you can actually listen to some of these sounds of the sun online on some websites if you look around. So here's the bell. Here is one of the modes at 1342 microhertz right here, and you see it has node lines on the surface where these parts aren't moving, but these regions are vibrating in and out. So this particular lower frequency mode has fewer node lines and fewer of these patches on the surface. And as you go up to higher frequencies, and all of these could be going on at once, you can have many overtones going on in a bell, just like you do in the sun. So as you go up to higher frequency, there are more and more node lines, and there are more and more of these patches moving in and out. So this is the 2600 hertz mode way up here. So these are different patterns that could characterize the vibration of this bell. So the sun is a sphere, more or less. So we categorize the different modes of oscillation in the sun by spherical harmonics. So this is an L of 1 mode. All of these modes could be going on at once. They've measured modes up to L of 1,000 on the sun, or even more. And we know all of these frequencies. So the L of 1 mode has one node line, and part of the sun is vibrating out while the other part's coming in, and then it switches. There's an L of 3 mode with 3 node lines and 2 lines through the equator, or through the pole, excuse me. L of 3, M of 3 here has 3 lines through the pole. So there's some degeneracies here. These modes have the same frequency if the sun isn't rotating, but they have a different pattern. Here's L of 5, 10, and so on. So spherical harmonics can help you characterize the angular dependence of the modes. So these modes also have a radial dependence. They're not just vibrating on the surface. The entire inside of the sun is also vibrating. So on the left, I show acoustic modes of the sun, and this is an eigenfunction for an L of 0 mode. So it's a radial mode. It's going in and out on the surface. The entire sun is moving in and out together. But the inside, there are actually many, many nodes inside the sun, all the way from the center to the surface. And the L of 0 mode actually propagates all the way to the center of the sun, has its largest amplitude near the solar core, and then a significant amplitude throughout the rest of the sun. If we look at an L of 10 mode, it doesn't have much amplitude in the center. It actually, if you just think about it as a traveling wave too, it basically turns around before it gets to the center, but it's sensitive to this further out region of the sun. L of 60 is sensitive to just the convection zone. It doesn't really get below the convection zone. So by looking at these different modes and their frequencies and using inversion techniques, mathematical techniques, they can back out the entire run of sound speed from the surface to the center of the sun very accurately. And there are also other modes that could exist in the sun. These are the gravity modes. They have a lot of amplitude at the core of the sun, very sensitive to the nuclear energy generation burning region of the sun, but they have very low amplitude at the surface. And their observation has not been verified to this day. So occasionally people try to find these in the data, and it's never definitively determined because they just have very low amplitudes near the surface. And they also don't tell you much about the envelope of the sun because they don't have much amplitude there. So after doing one of these solving one of these inversion equations for using the input of the oscillation frequencies, this is a picture showing the difference between the sun and a reference model that was actually constructed before the new abundances of the sound speed. So you see the sound speed was agreeing here with the reference model to within a couple tenths of a percent, the worst being right here at the bottom of the convection zone. It's actually not so good in the core either, but we have fewer modes that propagate into the core, so the error bars are larger in the core of the sun. But it's quite good in the determination is quite good in the radiative interior and even in the solar convection zone. These errors are, as you see, pretty small, and I think they've managed to get them even smaller. So this is showing a sound speed derivative. This is the equation that's actually plotted. It's a derivative of the sound speed squared versus radius. And you can see here, I think this is two different models. I can't remember, but it's basically showing that sound speed derivative changes abruptly right at the bottom of the convection zone. And this is how the bottom of the convection zone is located, is found. So this happens right at 0.713 in the sun, the change in the sound speed derivative. And that's because of it going from the radiative gradient to the adiabatic gradient in the convection zone. So that's known very accurately. And here's how they measure the convection zone helium abundance. Again, this is the sound speed derivative squared, and this is out in the sun's envelope. At around this radius at 0.98 or so, helium is ionizing. This is around 50,000 degrees. And this peak in the opacity derivative is caused by a peak in the sound speed derivative is caused by helium ionization. So by calibrating the height of this peak, the helium abundance of the sun is determined. Now these different lines here are for different equation of state models that this group tried looking at. So it does depend a little bit on the equation of state, but not on the opacity. Okay, so what happens when you put all this together? So we've made solar models now with both the Graves and Knowles mixture and the Asplund, Graves, and Saval mixture. And if we look at the sound speed difference compared to that inferred sound speed, here you see that with the Graves-Knowles mixture, we were only off here by a few tenths of a percent, mostly right below the convection zone and a little bit in the core, but that's a little more uncertain. And with the new abundances, it's not as good in a big part of the core, and it's about 1.4% or so different in below the convection zone from the inference. Now the convection zone is still off by a little bit, and this could reflect the helium abundance not being right, or the equation of state, or even some of the surface treatment here that could be improved. So there's more work to do also on equation of state and surface boundary conditions. Another thing you can do is look at the frequencies of the sun versus the model predicted frequencies directly. And this is the calculated frequency versus the observed minus calculated. And you can see with the old abundances, these are the red lines or the green lines, the observed frequencies and the calculated ones agreed to within 2 microhertz out of 2,000. So that's very, very good agreement, 1 part in 1,000. Whereas with the new abundances, the agreement for these different L modes is quite a bit off, 8 or 10 microhertz off. And as you go up to higher frequency, these modes have a little bit more amplitude in the atmosphere of the sun. And you can see here the difference that you can make just by changing out the low temperature opacities. Here we went from the Alexander and Ferguson 1994 low temperature opacities to the Ferguson 2005 opacities, and to the Alexander 05 opacities, excuse me. And you can see that slope downward is flattened out considerably. So these newer low temperature opacities that included more molecules and more lines actually did better. Okay, so now I'm going to go into the part of the talk where I'm going to show you a few examples of what we have tried to restore agreement between the standard models that are using the new abundances and the helioseismic inferences. So I'm going to show you some where I'm going to try some enhanced thermal diffusion. So this is the idea here is you start with higher elements, but then you let them diffuse at a faster rate out of the convection zone to get down to the lower abundances and see if that takes care of it. Accretion of low Z material. This is what if the sun formed with all of its heavy elements first, and then very late, after it started burning hydrogen, in fact, some lower Z material fell on top, basically, for the final bit of accretion of the sun's mass. That might actually help with making the agreement better. What if we included some convective overshoot? Would that help the agreement? What if we started the sun at a higher initial mass? There's some interest in that because that might solve the faint early sun problem, the problem with there being liquid water on the Earth earlier in the sun's life than the standard models would say, because the standard models say the sun would have been much fainter in the past. And also we find evidence of liquid water on Mars in the past that would be hard to do with the current predictions for the luminosity of the sun early on. And finally, I'm going to show what happens when you go to some new opacities. So the bottom line is right here. It's really difficult to match all the helioseismic constraints at the same time. So I'm going to start with this enhanced thermal diffusion. So what we tried is we tried lowering the thermal resistance coefficients in that Berger's formulation, and I actually cranked them down by, or crank them up if you want to think about diffusion coefficient, by a factor of 4 for a bunch of elements: carbon, nitrogen, neon, oxygen, and magnesium. And I didn't crank them down as much for helium because I wanted the helium to be higher in the sun's envelope, since that was a problem with the new abundances. So this gives you higher Z in the core, but it produces the lower photospheric abundance. I'm not going to change the gravitational diffusion because that seems like it would be more physically constrained. And I'm going to use different rates to avoid helium diffusion too much. So this is the best of those models. This is the one with the factor of 4 on the metals and 2/3 on the, or 3/2 on the helium. And what you see is that it does improve the agreement. Here's the new model with the enhanced diffusion evolved compared to the AGSO5 mixture. But the convection zone base is still a little bit shallow, and the convection zone helium abundance is still a little bit low. So, and also you could argue that these thermal diffusion coefficients are really ad hoc, and these changes, and they're not physical. So it's not a very believable solution to the problem. All right, what about this low Z accretion idea, where we start the sun's mass at about 0.98 of its current mass, and then we accrete basically the entire mass of the convection zone with lower Z material that's collected after the sun begins core hydrogen burning, and it's not convective anymore. That's important, otherwise the low Z material will just get mixed right into the core, and that wouldn't help us at all. And so we'll see what happens there. What we did is we did that in about 6 steps, 6 time steps, just to make the numerics work in the code and not make it too onerous to do the modeling. So what happens here is the Z abundance in the sun goes, instead of being this is the accretion model. Okay, so in the core, it looks basically the same. And in the envelope, though, we've taken the Z from 0.018 down to 0.0122, which is where it is with the new abundances. And we can play with what the helium abundance accretion is, but it has not changed very much right here from the old abundances in this model. So what happens when we do that? Well, it does fix the problems in the radiative interior, but when you start getting close to the bottom of the convection zone again, this model, after it's evolved, it's still settling hydrogen and helium out, and it still ends up with too shallow a convection zone depth, and the convection zone helium isn't so bad, but the sound speed agreement, it's better, but it's not really fixed. So convective overshoot, what if we just extend the adiabatic gradient region in the sun and extend the mixing down so we get the convection zone depth deeper? Wouldn't that help? Wouldn't that help mix up elements and mix the helium up again so that it would keep it high? And it turns out that when you do that, you just basically can move that sound speed curve a little bit better into agreement right at the bottom of the convection zone, but the rest of the sun's mass it still has the same problem. It still agrees with the curve from the old abundances. So just doing convective overshoot isn't going to solve this problem. And finally, here's a set of mass losing models where we start out the sun at 1.3, 1.15, or 1.07 times the mass of the sun. And we have the sun, instead of having 2 times 10 to the 14 solar masses per year mass loss in its wind, it's quite a bit higher in these. It's 6.5 or 3 or 1.5 times 10 to the 10 minus 10. These numbers are higher than what people find in sun-like stars today. So these mass loss rates are not really believable. They're too high compared to stars like the sun. So, and also the 1.15 and 1.3 solar mass, 1.15 and 1.3 initial mass models can deplete a lot of the lithium in the sun's envelope, and they end up not agreeing with the sun's lithium abundance. But 1.07 is a little closer to plausible. So we had this mass loss rate exponentially decrease, and then the sun's luminosity started out higher, and then it joins the regular standard solar models down here at about 2 billion years or so into its lifetime. So you see with regular standard solar models, they're only about 70% of the current luminosity of the sun when the sun formed, and that was what was causing the faint sun problem and the frozen water on Earth and Mars and those other things that geologists are trying to solve. So what happens if you look at these models today, after we've evolved them to the sound speed? Well, here's our AGS-05. Here's our Gravesnell's 93 model as before. This is the model with starting at 1.3 solar masses. Well, that one gets most of the way back in sound speed to the old abundances, at least to the sound speed with the old abundances, at least right below the convection zone. But this model is showing deviations in the core, particularly way in the core here in the hydrogen burning region. That is because this model actually burned a lot more hydrogen into helium early in its lifetime. So it's not agreeing, it did too much compared to what the present sun is saying it did. And then here's the intermediate one at 1.15. It still has a little bit of problem in the core, but it's not as good on the radiative interior. And here's the 1.07, where this is a fairly believable model from many constraints, a little bit high, maybe initial mass, but it just gives you a slight improvement below the convection zone. At least the radiative interior is not as bad. So let's see, where is it? I guess it's this purple right here. So it's not in too bad of agreement. And these models do improve the convection zone. The most extreme one makes the convection zone radius just a tiny bit shallow. The helium abundance is still low. So it doesn't fix all the constraints again. Okay, so now I'm going to wrap up here a little bit with what happens if we change from the opal opacities to the Oplib opacities from LLNL that were generated with the atomic code. These were published in 2013 to 2016 in Colgan et al. So these tables were generated for the first 30 elements of the periodic table, and they're available online. You can go to this website and you can even mix your own mixtures for these tables. The new Oplib release that includes a number of improvements, such as a more accurate equation of state, refined temperature grid, and a significant fine structure detail in the atomic physics. And these opacities were used here, were mixed by mixing the pure element Oplib tables under the assumption of electron temperature and electron degeneracy equilibrium using the TOPS code. So this summarizes what happens when I calibrate a solar model using the opal opacities or the Oplib opacities. And this time I'm using the newest abundances, the AGS-09, newer abundances, 09 mixture. So here's what I get with Oplib compared to Opal. I need a little less initial helium, the same initial Z because we're using the same abundances, mixing length's almost the same. The surface helium is going down a little bit, and that's not the right direction. The surface Z is the same because that's how I calibrated it, and the convection zone base radius is a little bit deeper, so that's going in the right direction. So what I wanted to show you is, well, why are these changes happening? So I'll show you first the sound speed difference. So here we see the AGS-09 with Opal, and here is the AGS-09 with the Los Alamos atomic. So the sound speed difference is actually improved with the atomic. It's not as in good agreement as it was before with the old abundances, but it's improved with the atomic compared to Opal. So why is that the case? And this was very puzzling to me, because if we look at temperatures in the envelope of the sun, where opacity shouldn't matter, and it doesn't matter, the atomic opacities are actually higher than the opal opacities, which is good. We thought, well, having more opacity would help the solar abundance problem. But if you look in the core, in the radiative interior of the sun, where the opacities do matter, the atomic opacities are, for the most part, a little bit lower than the opal opacities for the same temperatures and densities. So what's going on here? Well, it turns out that there is a difference in the derivatives, and that's what's making the difference in the solar models. This picture is showing the opacity derivative versus temperature, and this blue arrow here is showing the sun, where the sun's radiative interior is, right below the convection zone at about 6.3, all the way down to the solar center. And you see the opal opacities are, the derivative is pretty flat in that region, whereas the atomic opacities, the Oplib opacities, the derivative goes down and then it goes back up again. And here I'm showing a blow up of that. So this downward derivative is occurring near the bottom of the convection zone, and this upward derivative is happening right at the around 0.3 in the sun's interior, closer to the core. And if you look at that again here with this sound speed plot, you see that for the atomic opacities, right around 0.3, the sound speed difference compared to the inferred sound speed actually changes, has an inflection. It changes slope and it starts to go up, whereas it's pretty straight here for the opal opacities. And then here, right below the convection zone, you see again this turn with this lower value and this turning over right here. So this is reflecting a difference here at the bottom of the convection zone in the opacity derivative. So really it was the opacity derivative that made the difference in the sound speed for going to the Oplib opacities. Okay, there's a few more slides here showing that other people have tried just straight opacity increases, and they're finding that if you increase the opacities quite a bit over different ranges of the solar interior, you can improve the agreement. Sometimes you can make it worse in other places though. And you can try combinations of effects. You can try opacity and diffusion increases, or abundance and diffusion increases. This one is where they've done both. They've increased the abundances to a couple of sigma past their uncertainties and included a diffusion multiplier of 1.65. This was a diffusion only increase. So that's it. It helps, but it's a little bit contrived. And here's a case where this group did both a diffusion multiplier. They raised the opacities to within the uncertainties by looking at the difference between opal and OP opacities. And they also increased the abundances. And if you do all of those together, you can get back to the original. And another thing people have looked at is tried increasing just the neon and argon and a little bit of the CNO, because remember I said neon and argon are more uncertain. So they've tried that, And that also helps, but people generally don't believe these much higher neon and argon abundance increases. So these are the conclusions. The new photospheric abundances give worse agreement with helioseismology. Simple single changes in input physics or assumptions do not restore the agreement or are not physically justified. Combinations of effects may be more plausible, but they seem contrived, and they still don't completely restore the agreement. And the LLNL-VIDEO opacities do improve the agreement, but just slightly. And it's not because they're higher in the sun compared to opal, but because they have steeper derivatives. So we don't have an obvious solution to this abundance problem. I wanted to end with some acknowledgments. I want to thank my collaborators at LLNL over the recent years, Susanna, Katie, Chris Fonts, Premek Walczyk from Poland, who's a visitor who did the mixture for us, Ibrahim Farag, who's a student, David Kilcrease, James Colgan, and Chris Fryer, who gave us lots of suggestions. And I'd also like to thank Manolo Sherrill and Todd Urbach and the organizers for the invitation and the arrangements to present the talk. And finally, I wanted to thank Carlos Iglesias for pointing out at a conference to me in Santa Fe the new abundances so that I could start working on this again. I have one slide here recommending a paper that is fairly recent in 2019. It's an online publication in Frontiers in Astronomy and Space Sciences, and it's by a recent PhD student, Gail Bulgin, who won the IAU thesis prize in 2018. And it's a really nice review of the solar modeling, abundance, opacity problem. And you can see their bias solar modeling problem. This person is now working in Belgium with Gervais and Knowles. And so that may be part of the reason that they think it's a problem with solar modeling and not with abundances. So I would highly recommend this. And I'd like to go back to this question for discussion. Which is the actual problem? Is it solar abundances, opacities, or modeling? Okay, thank you.
Thank you very much. I invite everybody to unmute themselves and give a bit of an applause. And
maybe I will get out of slideshow mode so I can see something. I don't know if I can see anything, but okay.
it was a very nice talk, and I enjoyed it very much. And there are already questions rolling in, and feel free to enter your own. So Rich London asks, are there independent measurements of abundances since 2005 to 2009?
I'm sorry, could you repeat the question again? I was reading all these chat messages and not getting it. Go ahead.
Are there independent measurements of abundances since 2005 to 2009?
The same group has published some in 2015, which basically agree with the 2009. There's also some abundances by Cathau et al. Using this other 3D model atmosphere code, and they're a little bit higher, but they only did a few elements. So, and they use different lines, so it's hard to reconcile them. But yes, there are, but nothing has gone back up to what the original, what the older Gervais and Saval abundances have been.
Thanks. So Marilyn Schneider asked, it looks like measurements of abundances change with different measurements. Has the sound speed differences been measured more than once?
Yeah, that's a good question, because they found the sound speed from these reference models that were done a long time ago. So has this been redone? And I am fairly certain that this Gail Bulgin and his collaborators have redone it, and they're not getting a significant difference in the sound speed derivation.
And Rich London asked another question. Any ideas for laboratory experiments to address this problem?
I would like to see more done with oxygen, because oxygen is very abundant, as I showed you. And, it affects the opacities below the convection zone quite a lot. So some other elements in addition to iron, I would like to see measured. I'm reading a chat from James Colgan, who sent it to me privately, and he says that I used the word lead cop, and the 2015 opacities from Atomic were using the atomic code and not the lead cop code. And if I misspoke or have it wrong in my view graphs, I'm sorry, I will correct that. So these were all done using the new atomic code. Okay.
There are a couple of comments coming in that there are oxygen measurements planned for NIF. So yay.
Yes, I heard about that earlier. That's really good.
Yeah, it's done. This is Bruce Remington. Don Wingett has an accepted NIF proposal to measure oxygen on NIF.
Right. I would really like to see that. A number of us have been putting in proposals for that for a while. So, yes.
And Guillaume Lozelle asks, would you think the mass loss model improvement would give even more improvement with the AGSO9 composition? Are there independent constraints on the initial solar mass?
Yeah, I think that if you use the AGSO9, since it's a higher abundance, it will improve things compared to the AGSO5. But not a lot, a little bit. It's not going to solve the problem. Anything we can do to get higher abundances will help us with the problem.
Dwayne Liddell asks, are there any other G stars to which your models can be applied and tested against stellar seismology measurements?
That's a good question. You know, what are the implications of this problem, not just for the sun, but for other stars? And Gail Bulgin in his paper does talk about attempts to do astroseismology on other stars. The problem with those stars is that you can't measure as many frequencies. So it's hard to do an inversion of the entire star. There are implications, though, for the age of the star, and you may be able to get constraints on the star from other observations. Other stars probably have a different mixture as well, a different element mixture that would have to be measured. So it's harder with other G stars. There are groups that are looking at, for example, opacities and finding that B-type stars and Cepheids, for example, need higher opacities still, especially iron opacities, not in the area where it matters to the sun, because it's not as cool, but around 200,000 degrees and even maybe 1,000,000 degrees, it does help to have higher opacities for other stars. So that's pointing us towards maybe there is an opacity problem and not a abundance problem.
There's also a comment from Tai Nagiyama who says that they're also starting oxygen experiments on Z.
Great. That's good. And one question I have is, does it matter if you do oxygen or carbon or nitrogen? Are they all so similar that if you do one, it's enough? Because the other two elements are pretty abundant as well.
I don't know about the experimental differences or.
Yeah, I don't know. It's just a thought I have. Maybe even looking at other elements would be good.
Yeah, I mean, I think this is Bruce Remington again. I think the experiments could be done. The question is, pick one and start, because
Yes.
it's a hard measurement. You have to look at lower energies to measure the effects. If that looks like it turns out to be very valuable, then I think, yeah, your suggestion is good, since it seems to be such a big player. And, coordinating, or at least being aware of what we're doing at Z and Omega, Z and NIF is a really good thing to do.
Yeah.
So Bob Peter typed in that oxygen is easier experimentally since the lines are at higher temperature, as compared to nitrogen and carbon, which would require grading spectrometers. And Colgan also said carbon, nitrogen, and oxygen would probably be quite similar at high temperatures of relevance. So Bob Peter also asked the question, since the solar dynamo is also not fully understood, and more or less magnetized plasmas will have different sound speed behavior within the sun, is it possible that the acoustic eigenmode theory could be yielding incorrect conclusions about where the CZ should be, etc.?
Yeah, that's an interesting question too. So the only thing I have to inform that is by looking at the changes in the sun's oscillation frequencies over the solar cycle. So you can watch how much they vary, and they vary by about a half a microhertz out of 2000. And that's quite small. So we think the perturbations on the sun's sound speed in the interior due to magnetic fields, they're present, but they're quite small. They're not enough to change the inferred sound speed by much more than the width of those lines I was showing. So yeah, I don't think it's going to, I'd be wrong, but I don't think it's going to do it. But there is, magnetic fields the dynamos generating turbulence, and there could be pressure changes because of that. How important are those? Those are some of the questions I have. People have tried to include some of the turbulent pressure effects below the bottom of the convection zone. And again, it helps the problem by about 10%, but it's not enough to solve it.
There's a question from Guillaume Roussel. Has anyone looked into the combined opacity contribution for the other elements that are 1/3 in mass of the metals?
Yes, I did that. And I think I published it in a conference proceedings, and it makes zero difference.
Good to know.
I actually did the mixture with every element in, the lotters or, somebody's table with all the meteorite abundances. I put it all in, and it didn't help.
And there's a question from J.A. Bale. One question is whether iron opacity in a pure iron plasma is the same as when iron is a trace element in a hydrogen plasma.
Maybe someone else should answer that. It isn't the same. I mean, you do need to take into account the surroundings of the ion when you create opacities. And we do that, or we try to do it correctly in the TOPS code.
It's a tough modeling issue.
Yeah, you don't just take the opacity of iron and carbon and whatever and just add them together. You have to put them all together in the mixture and look at the electrons around it and how that's affecting the ionization levels and the pressure before you make your opacity table.
And he also said oxygen is easier than carbon or nitrogen. Bob is correct. However, that is different from saying oxygen is easy to measure.
Yeah.
And
a bunch more comments out there.
Yeah.
I keep reading all these comments. There's a lot
of nice little discussion going on.
Yeah. You should definitely archive this discussion.
Good point. And Bob Huter responded that's right, Jim. I should have said oxygen is slightly less challenging. And Peter Heckels said iron line shapes in hydrogen plasma could be affected by the ion dynamics effects and Stark broadening. And Ronnie Shepard responded, hi, Jim, since the density is not extremely high, I would not think it would play such a large role. But anyway, thank you all for all those comments. And nice to have a detailed discussion with everybody in person. And we can at least have this forum. And thank you again, Joyce Guzik, for the very nice talk. I very much enjoyed it. And I hope everybody else did too.
Thank you for the invitation. So I will send view graphs to you to put up on your website then.